Hello everyone, welcome to the lecture series on VLSI design. In the previous lecture, we had discussed on scaling of the MOS devices. So there we learned what is mean by scaling. So what are the impacts of scaling down the devices? So how it is going to be affected for any electronic device. So we even went through what are the factors which might be affected, so which we need to be considering when we are thinking of scaling down any devices. So certain factors might be, so we studied something like how the channel length is going to be affected, so how channel width is going to be affected, how the gate area is going to be affected, so etc. So all those factors we had gone through in our previous lecture. So in today's lecture we shall go to and the subsystem design. Subsystem design is nothing but if you are having any complex circuit. So usually the approach is we won't be jumping into designing any complex circuit. If we are having any complex circuit, we will be dividing in terms of sub simple circuits. So we will be designing better way. So how it is going to be affected? Okay. Lower unit cost, that means what? That means the amount, the cost should be as low as possible when you are trying to bring up any product. Higher reliability in the sense the circuit should be, the integration of the simpler circuit should be as less as possible. That means what? The complexity of integrating these smaller circuits or subsystems what we are having in order to bring up a complex circuit, the sub connections, these connections should be very much less as possible. So power dissipation is one of the factor which is affecting everybody. So the system what we are going to be designing, that should be low power consumption. So it has to consume very less power as much as possible. As a designer, one should look into the power dissipation factors so that his design will be consuming less power. Better performance, as we have seen in the previous class, by scaling down the design, we can improve our performance, or we can increase our clock speed. So we can have some higher clock speeds in order when we are scaling down in devices. So our system should be, our design, what we are going to design, it should be capable of going with the higher speed clocks. So time to market is one of the major important thing what we need to be considering, because there are so many competitors in the market as of now, and everyone will might be having any one of the design. But if suppose if you are having any idea, if that idea comes first to the market, then that company person will be in the profitable area. So time to market plays a very much important role in terms of what, in terms of designing the things. So what are the problems what you might be facing, or what we might be facing? So those problems might be how to design a large complex system in a reasonable time with a reasonable effort. So and what type of architecture is best suited for our design. The testability of large or complex systems once implemented in silicon. So what are the testability things what we need to be considering? So these are the problems where a designer where a designer might face. So there are some solutions. So some solutions might be, our approach should be top down approach or a bottom up approach, as we had studied in our previous semester classes. So we had gone through different types of methodologies, design methodologies, that is our top down design methodology and bottom up design methodology. So in top down, once a customer comes and gives certain specifications, what he needs, what his product should be, what his product should be. So a designer, what he will be doing, he will be coming up with a specification. That specification, he'll be coming up with some complex circuit. So that complex circuit will be divided in terms of smaller simpler circuits, and those smaller simpler circuits will be further divided in terms of what, in terms of leaf cells. So designing of these subsystems is the better way of approach is what? The better way of approach is a top-down approach with adequate CAD tools to do the job. So adequate CAD tools in the sense, when you are having designs, you need to have computer aided design tools or EDA tools to do the job, because there are different way of approaching the things. So one might go with in terms of FPGAs, or one might go in terms of application specific ICs. So one might go with in terms of HDLs. So we should have adequate tools in order to do the job. As we had said in the previous things, what are the general considerations? We had said that the time to market plays a very important role in terms of designing the things. So partitioning the system should be sensibly done. So we need, and higher reliability, we had said, that means the connections, what the interconnections should be as less as possible in terms of integrating the things. So interconnections should be very much less, and will come and he'll explain his specific design should be complex. It might be doing any addition or subtraction. So for that thing we need what we need, we'll be needing two operands, that is some value from A and then some value from B, and then we are going to perform those addition operations onto those two different things. In order to do those things we need some control signals where we can have those things, or where those operations will be done, and we need to have input output port, all these things. Okay, so here we will be concentrating only on this data bus what we are having. Okay, there are different, see in the previous slide we had said that which architecture might suit well for our design, there was a condition, right? So that we can overcome over here, how to choose a particular architecture for our design so that our design will be working faster and then it will be having a very good time to market. So here if you are considering in terms of data path, okay, the data path can be, you can go in terms of one thing for your data in operation, okay, one bus for input bus and one more bus for your output bus. Okay, there is one more way of approaching the design, is we can go for only one single bus, that single bus can be acted as an input port as well as output port. Okay, so this is one way. In the similar way we are having different types of bus topologies, or different types of bus connections where you can come across. Let us look into here. We need to have what, we need to have some basic interconnection paths. So from input it is going to be in terms of what, from input it will be going to the register, from register it will be going to the ALU where arithmetic operation will happen, and then the output of that thing ALU will be what, it will be sent to the shifter, from shifter it will be going to what, it will be going to output port. Okay, this is a normal nomenclature or normal structure what we can have in terms of 4-bit arithmetic processor. So let us look into some of the bus architectures where we can have how the things can be done. Okay, so the first thing is what, the first thing is one bus architecture. So if you look at the thing, so we are having the values will be stored in what, the our input values will be stored in registers. Okay, and ALU will be the arithmetic operation will be done at the ALU, and the output will be shifted, and then again it will be stored back where, it will be stored back in our registers. So from register, if you look at this particular architecture, the let me take a pen over here. So here if you look at from register to ALU, from here to here you need one cycle. Okay, so let me write it in terms of cycle. So here one clock cycle is required. Okay, and ALU might be operating, and then here shifting of data from ALU to shifter, there might be another clock cycle is required in order to shift data from here to here. Okay, again from shifter to the register, so our memory location, there might be requirement of one more clock cycle. Now if you look at this, only the movement of data from registers and then doing the operations and then again coming back to the register, or the for the storage of the result. The total required clock cycles are how many? So the total clock periods required are 3. So if you are running at suppose let me take my clock frequency as 10 megahertz. So the time required to complete this whole thing is what? So it will be uh, uh, 0.3 microseconds, because how we are going to calculate? Suppose if I am having a frequency of 10 megahertz, if you are we had said that time is inversely proportional to 1 by f. So if it is 10 megahertz, 1 by divided by 10 mega, so that will be 0.1 microsecond. So 0.1 microsecond into 3 clock cycles, that will be 0.3 microseconds. So one bus architecture will lead us how much? So it will be leading us in terms of 3 clock cycles. So let us look into another architecture. So that is 2 bus architecture. Here we have done a little bit change in terms of bus architecture. We had taken, instead of only one single bus, we have taken 2 different bus. So that is what? That is bus A and then bus B. So here there is a different type of thing. So here what you can observe is that our input bits A and B will be loaded at the same instant of time. Okay, that means here how many clock cycles are required? From register it will go on to A, and register it will go on to B, because there are 2 different buses over here, right? So I can use one bus for loading of input value from A, and I can use one more bus for loading of input value B. Okay, so total for loading of these things, total number of clock required are how many? So it is of only one clock cycle. So at only one clock cycle I can load the values into the ALU unit, and once ALU performs those operations, the number of clock cycles required to store back to what? To store back to this register is how many? Again it is one clock cycle. So here the total number of clock cycles required in order to complete the thing is what? This is one clock cycle and then this is one more clock cycle. So total 2 clock cycles, whereas in previous one bus architecture we had how much? We had required 0.3 microsecond, but when it comes to 2 bus architecture, the number of clock cycles required is 2. So if you are running at 10 megahertz, the time required to complete this particular task is only 0.2 microsecond. Okay, so if you look at this, the time is almost, it got reduced, right? Now because we had changed a little bit of our bus architecture so that we can achieve a higher speed. Okay, so there is one more thing. So this is what? This is 3 bus architecture. Okay, so we are divided in terms of since we had what? We had uh, a single bus for carrying our result. This result can be overcome over here. Okay, so we are divided to load our inputs to 2 different buses over here and load the output. So we are having one different bus. So loading is done over here. Okay, and operations will be done over here, and then the output will be done over here. So again, so since all buses are different, I can do the operation in what? In only one single clock cycle. Okay, so one single clock cycle I can achieve all these operations. All the data can be moved in terms of only one single clock cycle. So it has been reduced in terms of what? 0.1 micro. Our one bus architecture was leading us what? It was leading us 0.3, and our this thing was leading us 0.2, and 3 bus architecture, it is leading us what? It is leading us only 0.1 microsecond. If you look at this, there is a total time gap over here. Okay, So when you are changing different types of architectures in, see here we are not considering how does our ALU should work. Okay, here we are concentrating only on this, what, how our data should move from one place to another place. Okay, so by implementing these things, if you are having only one bus architecture, it was leading us a longer time period, whereas when we changed a little bit of our architecture in terms of 2 bus and then 3 bus, we can achieve what, we can achieve a better result over here, right? So here the architectural issues which can suit best for our thing, that can be decided by looking into these terms of things, by changing in terms of architectures where we can achieve a higher speed. Okay, so let us look into one more example, that is a 4-bit shifter. Okay, there we had discussed on our what do you say, where we had discussed on only the data path. Here we will be concentrating only on the shifter. Okay, any general purpose n bit shifter should do what type of operation? It should shift the number of places, n minus 1 places, to right shift or left shift. Let us assume that any bit shifted out at any one end of data word will be shifted in at the other end of the word. That means let me take for this particular thing, let me take a register which is of 4-bit of data. Okay, so here I'm having 4-bit of data. If I'm doing right shift, so this, the right shift in the sense this shift, this bit will be coming out. So this bit, whatever it is coming out, it will be sent as an input to my higher bit. Okay, from this what we can achieve is that it can be analyzed that for a 4-bit word, that 1 bit shift right is equivalent to 3-bit shift left, and 2-bit shift right is equivalent to 2-bit shift left. Okay, so considering this, a shifter must have 4 input from a 4-line parallel data bus, 4 output lines for the shifted data, and means of transferring input data to the output lines with any shift from 0 to 3 bits. Let us consider that we are having totally 3 number of shifts, that is 0, 1, 2 and then 3. Suppose if your shift is 0, then your output value what you are having, it is same as what, it is same as your input bit. Now if you look at one more thing over here, here you can have, if it is shift 1, here it has been shifted left. Okay, the final output is loaded with what, it has been loaded with our the first value. Okay, and everything has been shifted left. In the similar way, 2 bits have been shifted left and then 3 bits have been shifted left over here. Okay, so how you are going to design these things? If you are looking in terms of any CMOS technology, we will be looking in terms of what, we will be looking in terms of pass transistor logic. So pass transistor in the sense, when the switch is on, we are going to transfer this particular thing to what, we are going to transfer this particular thing to our output channel. So if this is your input, input will be sent to the output based on this switch. Now if you look at 4x4 shift, total number of switches which are available are, switches will be varying from SW0 to 16, 15. So total number of switches are 16. So if you look at this, the design complexity or the complexity of in order to coming out with a shifter becomes little more complex. So what we need to do, is that we need to combine different switches and then we need to perform the operation. Okay, so combining the things is nothing but what, here let us look into this particular example. Combining the things is nothing but I'll be considering two different things. So what is those things is, I'll be grouping the things in terms of four different groups. So those four different groups will be, I'll be grouping one group for what? I'll be grouping one group for shift 0. I'll be grouping one more four groups or four switches in terms of what you say, for shift 1 I'll be grouping four switches for shift 2. I'll be grouping four switches for what again, shift 3. Okay, so you can see this is the normal thing what we are having. If you look at the if you look at the designing part of this, you can look at this particular option over here. Here we were having only what, here we were having only this pass transistors for where 16 different pass transistors we have grouped in terms of this. Now shift 0, if you look at this, the shift 0 is being connected to here, and then again it has been gone to where, it has been gone to this particular design you can see over here, and again it is connected over here, and again it is connected over here, and again it is connected over here. Okay, so one more what we can have is, if you look at shift 2 operation, now here this is connected over here, and then over here, and then over here, and then again over here. You can see this path, this has been gone through something like this. Okay, so let us take one more example, one more this thing. If you look at this, it has been connected like this, from again it has been gone like this, and then like this. Okay, now if you look, if you think this, okay, let me take this as a thing. If you look at this, this is just like a staircase what we can have over here. Okay, since your this thing is in terms of your input signals what you are having, if it is in terms of these values, you can find a staircase pattern over here. So this type of staircase pattern, or this type of assigning the inputs, we can call it as what, 4x4 barrel shifter. Okay, so here let us go through this barrel shifter in depth a little bit, so how we can achieve the normal shift operation. Okay, so let me take this thing, we are having what over here, we are having, let me consider shift 0. So whenever you are having shift 0, your output should be same as your input, right? So here we are having different inputs, IN0, IN1, IN2, and then IN3. We are having these outputs, output of 3, output of 2, output of 1, and output of 0. See, whenever I am applying shift 0, okay, this particular transistor is on. So I'll be using different colors for different shift operations, so that you can come to know that which and all transistors are on. See, when I have applied shift 0, this transistor is on, and this transistor is on, this particular transistor is on, and this particular transistor is on. So when you are having this particular transistor, here you are having IN0. So this output will be what, it is output of 0 will be again IN0. Okay, now this particular transistor is connected to where, it is connected to IN1. So this is what, output of 1 will be connected to IN1. This particular transistor is connected to what, it is connected to IN2. So output will be what, it will be IN2, and this particular transistor is connected to IN3. So here 0 bits have been shifted, that means no shift has been occurred. Now if I want anything shift, I want shift my this thing to be shifted, what, it should be shifted by 1. So what we can have, so here if you look at this, Now when you are having shift 1 over here, so that means what? Here your this thing is connected, here if you look at this particular shift, you can observe, so this particular transistor is high, so here what you can have, here you can have IN1, and then this particular transistor is high, what you can have, you can have IN2, right? So and then here this particular transistor is high, so you can have what, here you can have IN3, okay, and then this particular transistor is high, so you can have IN naught, okay. In a similar way you can have, let us look into different thing, okay. So when you are having shift 2 operation, so this particular transistor is high, so it is what, it will be IN2, and this particular transistor is high, so it will be IN3, okay. Since here you can see this particular transistor is connected to what, it is connected to IN3 over here, and this particular again it is been connected to what, it has been connected to this particular transistor, so your this thing will be what, out of 2 will be IN0, and here when you look at this, your output of 3 will be what, it will be IN1, okay. In the similar way when you are having shift should be of 3, so here this particular transistor, so it is what, it is this transistor is connected to IN3 operation, so this is IN3, and again it will be where, it will be coming over here, so it is what, it is again IN0, and this particular transistor is on next, so it is IN1, and this particular transistor is high, so it is what, it is IN2. So if you look at the truth table, it is performing as if there is a shift. Now if you look at this, whenever there is shift 0, so there is no any operations, right? So here it is no shift at all, but if you look at this, there is a left shift by 1, and if you look at this, there is a left shift by 2, and if you look at this, there is a left shift by 3. So this is nothing but this is designed with the simpler circuits. Those simpler circuits will be integrated in order to come, we will be coming up with what, we will be coming up with the complex circuits. And one more thing is which type of architecture which will be suited best for our design. So based on the changing of the architectures, we need to go for which is better suited, or which is the best for our particular design, so that we can achieve maximum number of speed.